All right, so I don't even want to pretend like this next little slide part to our presentation is going to describe what it really defines here in terms of the term quantum theory. Quantum theory is crazy. Quantum physics, quantum mechanics. When I say crazy, I don't mean it's mind blowing, but you could spend years on dealing with quantum physics and the way that light moves and how particles moves, and when you get into like photons and whatnot. I am going to just barely brush on it, and what I want to talk about is how energy is related to light, or how energy is also related to the electromagnetic waves. So for our purposes, let's just know that this deals with energy. Okay? And please, if you're interested in getting into more and more quantum physics and quantum mechanics, do so. Explain it to me. I'd love to know more and more, but for our purposes right now, at least, until we get into more detailed chemistry, we're just going to know that quantum theory, for our purposes right now, deal with energy. Okay? So, since it deals with energy, we're going to take a look at Planck's theory. Planck's theory is this is a scientist that deals with this quantum theory. He noticed that energy is related to the frequency of the wave. So if you have something with a very, very high frequency, it has a lot of energy. A wave that has a low frequency would have very low energy. And so Planck's theory basically says that the higher the frequency, the higher the energy. The lower the frequency, the lower the energy. This is a direct relationship. And notice that we can also tie that into wavelengths, because a low wavelength meant a high frequency, and a high or a long wavelength meant a low frequency. So again, now if I talk about a wave that looks like this versus a wave that looks like that, this one on the left has a low or short wavelength. Sorry about that. Let me just circle it. This one on the right is the one that has the short wavelength. So that's this one, versus one that has the long wavelength, which is this one. So the one that has the higher energy is the one that has a shorter wavelength. Okay? And Planck's theory, since it's a direct relationship, energy and frequency, he uses a constant, which basically Planck's theory or formula is energy is equal to the h times the frequency, where of course E is energy, h is Planck's constant, and of course this is frequency. All right, now frequency we can solve using that other formula. Planck's constant h is 6.6262 times 10 to the negative 34th joules seconds. Joules times seconds. That's the constant right here for h. And notice, since h is a constant, and this time if this h remains constant, if you increase your frequency, you're going to be multiplying by a larger frequency. You're multiplying by the same constant, you're going to get a higher energy. So that's why it's a direct relationship. Okay? Obviously, the one we just solved, I think on the previous slide we solved for the wavelength, the frequency as 5.71 times 10 to the 14th 1 over s. All we would need to do with that is multiply it by the h, and we would get our energy. Okay, I do want to solve one of those problems real quickly here while we've got it on the screen. And what I'm going to do is I'm going to solve it going all the way back to my wavelength formula. So because we know the energy formula, and because we know the speed of light formula, they both have frequency in them, then we can use them together. If I give you the wavelength, that would be the only variable that I have to give you, because this is a constant and this is a constant. If this is given, you can solve for the frequency, plug it into this one, multiply it by a constant, and solve for energy. And so that's what I want to do real quickly. Let's say, and I'm going to just rewrite my formulas. Let's say that your wavelength is given as 6.95 times 10 to the negative 7 meters, and I want to know what the energy is associated with that. Again, notice that you're given this one. You can solve for the frequency, since this is also known, it's a constant. Once you know that and you know your constant h, you can solve for your e. I guess that's kind of the idea. You're using the two of them together. Let me go right ahead and rewrite this equation. Frequency is c over the wavelength, which again here, 3.00 times 10 to the 8th meters per second over 6.95 times 10 to the negative 7 meters. I'll go right ahead and punch that into my calculator right away. 3.00 EE times 10, don't do it, just EE, that means times 10 to the 8th divided by 6.95 EE negative 7. I get a frequency of 4.31 times 10 to the 14th, 1 over S. I'm now going to go ahead and solve for my energy, which, notice, 6.6262 times 10 to the negative 34th joules seconds multiplied by my frequency, what I just solved for, 4.31 times 10 to the 14th, 1 over S. I've got that already on my calculator, so it's times 6.6262 EE negative 34, and I get the energy associated with this wavelength is 2.86 times 10 to the negative 19th joules. Notice my label makes sense that it's in joules because my Planck's constant is joules seconds, frequency is 1 over seconds, so those seconds cancel, and it makes sense that we get joules, and that's a unit for energy anyhow. So there's Planck's theory in practice in terms of our calculations. That's kind of how we would solve it.